Good morning, everyone. Uh, while I'm thinking about it, let me go ahead and get my Google calculator. That's our calculator of choice for our class. And again, the calculator is a convenience when we need approximations. And again, I'm reminded of what I actually have to teach in Calculus 2 when we start talking about Taylor's theorem and how we evolve these functions that we're studying into infinite series. And then you get the first idea as to how a calculator actually works. It's a computational tool based on infinite series. So the premise behind what we do is arithmetic, basically. And so when you do calculus, you're doing a fundamental arithmetic. Uh, and so the nice thing about the calculus sequence is that you start to learn what math is all about and how technology works, because you basically have all this coding that affects the actual arithmetic to give you the results that magically seem to appear with your calculator. So we certainly are indebted to the technology. Otherwise, we'd be using tables and slide rules. And so, again, I remind you that the use of the technology is to support what we do, not a substitute. So, what I want to do today is to finish the ideas from the law of cosines, which I didn't have time to do last time, the justifications, because they're very important. What you're seeing is that this work with the law of sines and the law of cosines and all the extra stuff with it actually helps you to solidify the fundamental material that preceded it. So it actually is good review. And then once I complete that, I want to cover a few topics of review just to kind of help you put everything together. I always think the first test in trig is not very difficult because they're just very fundamental concepts and not things that are overly challenging, like maybe the last test that we had at the end of the college algebra. So that should give you somewhat of a lift. So what I want to do right now is go ahead and share my screen and do a justification of the law of cosines. Again, we're finding that when it comes to uh, the triangle interpretation of trigonometry, we are definitely happy because it affords us an understanding that's very, very fundamental to what we've done in our previous courses, especially in geometry. We see that when we get into calculus, not only do we use the algebra, not only do we use the number theory, all of that, we the use of geometry and also trigonometry is central. It's like everything you ever knew, you just put all together and you use it as needed. So again, I think that this justification will be helpful to you. Remember, for the law of cosines, I'll just write one of the forms down that actually comes up often because we start with the letter A. Remember, our generic triangles will always be labeled with the lowercase letters for the sides and the uppercase letters for the angles. That will be standard from here on out. So that's the way we will keep track of triangles without going absolutely crazy. So one of the forms that we used yesterday of the law of cosines looks like this. So we have, in this particular case, let me get the right angle here, and I'll show you how we remember this. As we write the law of cosines, we can kind of think that if we had a right angle, we would have the Pythagorean theorem. So solving right triangles is fairly simple, fairly straightforward. But to correct for the lack of a right angle, we have this term. And like I said before, if you look at this, again, when I write these things down, I need to stop talking so much and get the letters right. There we go. I'll go ahead and write down the other one so you can see. You have your lowercase letter here, and the uppercase corresponds to that for the cosine. And then the other two letters we see in the first two terms and in the coefficient of the cosine of the angle, the BC. So BC is repeated here with the -2, and then the lowercase a and the uppercase a. Then we can do B squared, A squared plus C squared minus 2AC cosine B to mimic this. And then we can do C squared, A squared plus B squared. That's what I was trying to write, I think, 2AB cosine C. So when we think about the law of cosines, just like the law of sines, we can mix and match the letters depending on what we're given in the problem. And again, drawing that generic triangle always helps us to orient the three parameters that we're given. So what's interesting is that when we have a right angle, or in our triangle, a right triangle, we already have one of the angles. So that's a big plus. So we don't need as much information to finish the problem. So because at that point we can use trigonometry to solve for angles. And then of course, once we have two angles, the third one is a given. So with the standard generic triangle, we need three pieces. With the right triangle, we can operate with less. Again, keep that in mind because that helps you to solve problems as you work through this course, and also helps you to solve problems as you may see them in physics class or an engineering class that you may be taking with Dr. Nate Wiggins, who is my colleague. I think you all will have a good time with his classes. They are very interesting, they're very challenging, but they use all of the mathematics that you have been cultivating since high school or even general math. You know, it's funny, we use general math so much, it's like my goodness, as we combine numbers, as we factor numbers, that's all general mathematical concepts that basically is the basis of number theory. So maybe we should call general math number theory and give it a higher status because general math, I think, makes it seem as though it's not important, and it is extremely important. So let's look at a way. We're going to do two cases here. Let's the basic thing in doing an analytical geometry proof is to set up a triangle in the axes so that we simplify the algebra. So I'm going to start with an x-axis and a y-axis. We're going to make this as simple as possible. So this is going to be case one. And this will be good practice. This will remind you of the derivation for the area of the triangle, which is an important formula. So now we're going to take vertex A to be right at the origin of the coordinate system. So this we will label it A, and we'll put its coordinates 0, 0. And then we'll just extend, and it doesn't matter how you configure the letters. I think I'll just put the C here, it doesn't matter. And then we'll label it once we figure out what its distance is. So here we'll have C, and then we can go ahead and draw the other vertex. We'll just call it B, of course, and extend from the other vertices to draw an acute triangle. So here's B. And then, of course, the length here would necessarily be B, the side opposite. And so that's going to give us a coordinate for C, B comma 0. So those are easy. The only thing that we have to think about, ladies and gentlemen, basically are the coordinates here. So we need to figure that out. Now, one thing we'll notice is that we have angle A here. So we have side A here, and then we have angle C here. So we have side C right there. So this is our generic triangle set up so that one of the vertices is at the origin. When we do conic sections, we'll do the same thing. We'll define the conic section, and then we'll orient it in such a way that we simplify the algebra. And again, these become universal conventions. Universal. Your physics professor, your engineering professors will always say, if you're going to use the plane, make sure that you configure whatever figure or drawing that you have in the most simple way. And again, that simplicity makes your calculations easier. So what we want to do is drop the perpendicular so we can get a height of the triangle. And we'll just call that H. So we have an H here. Now, the portion of this part goes right back to our definitions of the trig functions with the right triangle. So here's what we can do, and it doesn't matter if you think of this way or whatever way. I'm going to go ahead and label this distance here. I'll do it up here so you can see it. This will be distance X. And then the distance from here to here, we're going to call Y, like we're using a terminal point on the unit circle. So now we can use our definitions for the trig function cosine and sine. So now we look at angle A here, we can think of adjacent over hypotenuse. So this implies that the cosine of A is X divided by C. So then we can actually solve for X by cross multiplication. Very simple, but very important. And now we can use the sine. Again, the sine of angle A is the opposite side divided by the hypotenuse. So this gives us good practice using our right triangle definitions. So again, we can solve for Y. So we're getting the coordinates of B. So Y equals C times the sine of angle A. So now what we can do is we can go right over here and fill in the coordinates. That is, we have the X coordinate and the Y coordinate, and the signs are correct. This is an acute angle. So we have C cosine A, C sine A. That's why I wanted to do this, because this is excellent review. And I will often do a justification when it has some academic foundation to it. For instance, in calculus, I'll often do proofs that help the students understand how to use it. In some cases, the proof may be very beautiful, but the application and the proof don't always coincide. And so I may have to emphasize the use of it first before I go back to the proof. And that's exactly what I did here. Now we can look at this and say, okay, so we've got all these coordinates here. How does all of this fit together? Notice when we draw this H here, we form a right triangle, okay? And so we have an application that's available to us. That is the Pythagorean theorem. So when I said this was a generalization, that's not the best way to always preface it. Is to say, okay, here's what we have. It looks like a generalization, but as we do our work here, we see we can now utilize the Pythagorean theorem to actually prove this result. And the result ends up looking like this, where we basically extended the Pythagorean theorem. So it's not a circular argument, it's an argument that utilizes what we know about right triangles. So I want to make that very clear. So now use Pythagorean theorem in a direct sense. Of course, all of these definitions are dependent upon the Pythagorean nature of the unit circle. So now we're using the Pythagorean theorem in a very algebraic sense, you know, the standard one where we take the hypotenuse squared and set that to the sum of the legs squared. So now here it is. And if you want, just kind of, just put a little larger triangle around it. That's where we're going to use it, for that right triangle. So now let's go ahead and fill it in. And we'll just write it down here, and I'll do the other one on a separate sheet of paper to spread it out. So we have what? A squared. Well, let me start over here so I don't run out of room. So we have a squared, which is the hypotenuse squared. And notice the length here, we have to do a little bit of algebra. This length, and I'll just put it here, will just be b minus the coordinate x here. So here we have b minus c cosine a. So this is a leg of right triangle. Now the other one right here, the other leg is easy. It's just c sine of a. That's simple. The other leg is easy. It's already given to us. We've computed that. So now we have leg squared b minus c cosine a. And I'll just go ahead and write this down. We'll just call this first leg, and then we'll say that c sine a, second leg. So then we have plus c sine a. Now, though this is very simple, once we set this up, it's all dependent on how we configure the triangle relative to the axes. Otherwise, this could be a very challenging argument. We've made it so simple that we can actually see what's going on. So our figure here helped us to organize the mathematics. So now we can just go ahead and expand everything and see where that gets us. So a squared, so expand the binomial, b squared. So of course we're going to get that famous last term, 2 times the product of these. So that'll be a minus 2bc cosine a. So we think we did something right with this term. So that's giving us that. So that looks really good. And then we square this term, we get c squared cosine squared a. And the last term is pretty simple. We just square it, c squared sine squared a. So now what we can do, it looks like we've got all the ingredients. We're just going to combine this by factoring. So we have b squared plus c squared, and then we have a cosine squared a plus a sine squared a. And then our last term, our straggler, minus 2bc cosine a. And of course, we have an a squared here. You don't have to repeat that, but it's very simple to rewrite. And of course, here's our fundamental identity. This is the Pythagorean. We have 3 forms of the Pythagorean identity, and they're extremely important because everything just basically blossoms from those identities. And so now we get the one that we need. So if and only if a squared equals b squared plus c squared minus 2bc cosine a. So at least for this acute triangle, and again, this is symmetric. You could just permute these. You could put b here, you could put a here and c there. It's all symmetric. So the argument doesn't have to be done 3 times. This is just a symmetric permutation, or a permutation of the coefficients, so to speak. And when you permute them, you get this. You just kind of, you're like standing in a line, and then the person at the beginning goes to the back and everybody shifts up. That's like a permutation of the person standing in a line. So the key here, and it's what we think of as being cyclic, because if you made a circle, it's just like shifting in a circular way. So again, when you take your probability courses and your discrete math, for all you computer science nerds that are going to become our future computer engineers, you'll spend quite a bit of time with that, and it's a lot of fun. Okay, so let's look at the second argument. So this is good to work through, and then it helps you to review the ratio definitions of the trig functions. We find those to be extremely useful, and how convenient to make a rule about triangles based upon trigonometry that really does depend on our second interpretation, the right triangle interpretation. So now let's look at the second one where we have an obtuse triangle. So you can see why I didn't start with this. I went to the examples because this is a little bit more complicated than some of the proofs we've done. It's not hard though. It's just you certainly get a whole lot more out of it once you do a couple of examples. So now we'll go ahead and draw the axes like we did before. We're going to set it up the same way. And when I mean set it up the same way, I'm going to keep the same configuration of the angles, but we're going to draw an obtuse triangle. And there really shouldn't be any difference, but just like when we did the area set up for the triangle, we do need to consider that case. Now, there'll be times when we're just going to focus on reference triangles when it comes to certain arguments, but here we do need to think about this because we're considering generic triangles. So in this case, to be lazy again, we're going to put the vertex A right at the center of the coordinate system. That won't change. We don't want that. We don't want that to be any different. And now we'll do the same thing with the C. The C is going to go right there, but the B will be over in the second quadrant, like right here, to make the obtuse triangle. So we have an angle that is greater than 90 degrees. So let's go ahead and draw it. Okay, not Rembrandt, but it will do. So we have B here, and of course we're going to be like, okay, what are the coordinates, just like we did before. So now, of course, we have the opposite side here, B, and so we see we're going to get another right triangle on this side, and we'll do the same kind of analysis. A is right here, so this will be A. That's going to end up being the hypotenuse of the right triangle that we formed. Of course, we've got B here, so this is again B comma 0. And then we've got question marks here. So the idea, and of course, if this is uppercase C, this is just C right here. So we'll just put that length as C, okay? So thinking about how we did the argument for the area, this looks very, very similar, right? So, but we're focusing more on the coordinates because the law of cosines is just a little bit more complicated. We need the coordinatization to make the problem work. So we're going to drop the perpendicular here to create a right angle. So right here. This is something you do in physics all the time. So this is really important. You love similar triangles in physics. I mean, that is just a mainstay. So now when we look at this, we're thinking, okay, if we can find the X here and we can find the Y here, that will give us the coordinates of B. And notice, ladies and gentlemen, that in both of these in both of these situations here, we had a point in the first quadrant, and now we have a point in the second quadrant, which we really had for the area formula, but we didn't need the strict adherence to the coordinate axes. So what I'm going to do is what I did before. I'm just going to call this distance X so we can give it a label. Choose whatever letter you like. It certainly doesn't matter. And we'll give this distance in this particular case. And you're thinking as we do this one and we think about what the actual coordinate's going to be, we see that the H and the Y coincide. So I'm just going to do this and just say this is our new Y, so to speak. So Y equals H. So that was a little bit different there. Now, If we find these two guys, then we've got the coordinates here. Now, this is where we have to think a little bit more. It's a little bit more complicated. Notice this is angle A here. This angle is in the second quadrant. So we'll say angle A is a second quadrant angle because it terminates there, okay? And so by definition of reference number or reference angle, that's what we have right there. That's the reference angle right here that's supplementary to it. And so then we'll say A hat is pi minus A, or 180 degrees if we're doing our direct calculations. We'll just go ahead and use pi now. So this is, and as we label, I'll use blue here. This angle is just A bar or A hat. And I'll focus here to remind you, this is A, okay? So we have to use A hat here, but notice what's important here. The cosine is less than 0 in the second quadrant, but the sign is positive. So we'll have to remember that negative sign when we do the computation for x. So let's do it. So now, using trigonometry, we're going to say, okay, cosine of, here's our right triangle right here, the smaller one. And then, of course, we've got the bigger one right there. So cosine of A bar will now be the negative of cosine of A, because again, this is in the second quadrant. So this is the negative of cosine of A. This is really good practice. I thought this will be great review for my students. And of course, so we interpret the reference angle in terms of the given angle of the triangle, which we need. We don't have cosine of A bar in the formula. We have cosine of A. And so now this will be adjacent over hypotenuse. So again, adjacent over hypotenuse. So we get, in this case, x divided by c. If and only if, now we can solve for x. X equals the negative of c cosine A. So I'm going to go ahead and write that in right now. The negative of c cosine A. And then I'll put the comma here. Now when we look at this, we're thinking, okay, well, this is looking good. Let's try for h or the y. So sine of A bar. Now, of course, remember in the second quadrant, the sign is positive. So the A bar sign and the sign of A are the same. No sign change using the arithmetic of the unit circle. So you're seeing even in the abstract, the arithmetic must be respected. If you don't respect it, then your work doesn't make any sense. It's like using an inverse trig function and you don't bother to respect the definition. Then you're writing down nonsense. And I say that because we're so used to having functions that are defined for all real numbers, save one or two numbers where they're undefined. And we just get so used to that, thinking, well, every function's that simple. Well, it's not reality, okay? So now we think of sine A, and we think in this case, opposite over hypotenuse. So this is basically, we'll just use the y over c. If and only if y equals c times sine A. So we can go up here, c sine A. So it's very similar to what we've already done, except when we have the obtuse case and the actual B is in the second quadrant, the cosine is negative and the sine is positive. You know, the sine function is really odd, and the cosine function too. You would think they'd be so much closer together since they're just shifts of each other, but there's enough complication there that we need both of them. We can't do without, you know, we have to have both of them. We can't manage if one of them decided to leave town. We got to have everything together to make it work. And so now we have a larger triangle right here. Here's the larger right triangle right there. So use Pythagorean theorem. Now notice this length here is really odd looking because it's got a negative sign in it. So when we do this, this is actually the negative of C cosine A plus B. Again, this is a positive quantity since cosine of A is less than 0. So if we didn't have this sign here using the reference angle, then this would be incorrect. Okay, so the beauty is here is that distances for a triangle are side lengths are non-negative or just basically positive. So use the Pythagorean theorem. So we're going to do, okay, here's the hypotenuse right here. So we have A squared. And then we'll have now I don't have to be so particular about this. This is one of the legs right here, and the other leg is right here. So we get what? Minus C cosine A plus B squared. And then, of course, the other leg is this guy right here, which is C sine A. So it looks very similar to the last one, but with a very important change. So we square A squared. So we square this, we get C squared cosine squared A. Now we take the product and hit it with a 2. So we get the minus 2BC cosine A. Square this. So now it looks just like the last one, sine squared A. Put these two guys together. So now we've got, in this particular case, let's see, and also, my other B squared, I kind of left it out like I thought it wasn't important. Let's square that too. Let's not leave him out. He's very important. So now we've got B squared, and then we can factor here, plus C squared cosine squared A plus sine squared A. And then, of course, the straggling term, minus 2BC cosine A. So, of course, this is equal to 1, our fundamental identity of trigonometry. So A squared equals B squared plus C squared minus 2BC cosine A. So I think that this kind of helps you to see how we respect the arithmetic of the unit circle, even when we're focused on triangles. We can't forget it. We still have to abide by it. And due to similar triangles, it doesn't matter how big the right triangle is. The ratios will always be the same. And that again is one of the luxuries of you having studied geometry. So when we talk about similar triangles, at least the application of it, that makes sense to you. So again, I wanted to now that you're at a level where this actually makes sense, you can see how we just go right back to chapter 5 and use everything in it. And then we use the new stuff from chapter 6 and we just toggle back and forth because both of them are independent, at least in terms of interpretations, but they're connected in the sense that they're equivalent. They have independent uses, I should say, especially here. But then as we delve into the algebra and the arithmetic, we see that we have to jump back to the unit circle and think about what's going on there. So this is good. If you go through this, I think the test will be very simple because this highlights the major ideas of what we've been doing. Now, the other thing that we did, and you probably thought I just made up Heron's formula, and I didn't. I didn't make it up, even though you might think I did. So Heron. When it comes to this formula, this is probably one of the most unusual formulas in the sense, if we define for our generic triangle, the semi-perimeter. And then we can think, let's just go ahead and think about a generic triangle, just like we were doing the law of sines or law of cosines. And it doesn't matter. We'll just focus on C this time since C is easy. And so we have lowercase c, lowercase a, and lowercase b. And we'll just focus. I'll go ahead and say here, this is where our focus will be. So you're thinking, if this is in the setup where we actually introduce the law of cosines, is Heron's formula dependent on that? Well, I will say this, ladies and gentlemen, when Heron derived this, he was not using ideas of analytic geometry that Rene Descartes invented that we're doing now. So I'm not really so sure of the history, but his methods certainly would have been very different from this. The Greeks came up with all kinds of elegant mathematics that just blows our minds. We're like, how did they do this? I mean, and it all turns out to be correct. I mean, as they continue to study the works of Newton, it's all correct. As they continue to study the works of the Greek mathematicians, all correct. And Srisvani Ramanujan, I mean, as they get through his work, which he put down in 2 volumes, all correct. So we're lucky that we had a lot of smart people precede us, and we're still using it. And soon, or after we're long gone and we've done it, made our world better, others will continue to use this mathematics. So the idea is that we got the area of the triangle, we'll just call that A, was the semiperimeter times semiperimeter minus A, semiperimeter minus B, semiperimeter minus C, all square rooted. And you're thinking, okay, that's a fascinating result. And we used it. Now, the idea here is that this will remind you of what we did when we did the proofs of the solving the triangles, which are basically proofs with the law of cosines. And this is what we're going to do now. So now we're going to start out with the square of the area because we're lazy. Usually in mathematics, if the result has a square root, focus on the square. Just focus on, just like when I was doing the problems, work it down, make it simple, make it as simple as you can, then apply the square root, or then apply the inverse trig function. Keep the work simple. Don't drag along things that are just going to get in the way. That kind of attitude about mathematics can be very time saving and keep you from losing your mind, so to speak. So now we can say, all right, how do we get the area of this triangle if all we knew was the formula that Professor Ron has proven in chapter 6, which you've used in your homework? We would say use the angle, the included angle, and the sides. And so we can say this implies that a squared will just be the square of, so we'll do 1/2 AB sine C. Usually we would say theta, but we'll call it C because it's a generic triangle, and square it. So we know that from what we've already proven. And then of course, we're going to replace, once we figure out how to wedge the cosine C in there, we're going to use the law of cosines. So now what is this? This is 1/4 A squared B squared sine squared C. And you're thinking, so that's the beginnings of this, and it is, and it's a very good beginning. So here's what we're going to do. This is also like doing an identity proof, but it's not quite an identity. We use the same kind of techniques. So if we needed to rewrite this, we could use the fundamental identity. So we'll say 1/4 A squared B squared times 1 minus cosine squared C, fundamental identity. There's our cosine, law of cosines type thing. So at this point, all we've done is use what we already know, and we're thinking somehow magically we'll get to this, and it'll be a lot simpler than you think. So now first what we'll do is we're just going to rewrite this as a difference of 2 squares in factored form. So this will be 1/4 A squared B squared 1 plus cosine C 1 minus cosine C. Okay, now this is where we have to infuse the law of cosines and then do some algebra to get to this formula. And this is very important because algebra is important in calculus and it's important in your ability to verify identities. So first, let's just go ahead and take this triangle and use the formula that involves the C, right? It's the standard one, the C squared one. So we know, let's do our little sidebar right here. Here's a sidebar. So we know C squared equals A squared plus B squared minus 2AB cosine C. That's exactly the type of formula we were using when we were solving the triangles. Remember I said transpose, take this to the other side, take this to the other side and divide by 2AB. That's exactly what we're going to do now. So I prepared you for this at our last lecture. So if and only if cosine C equals A squared plus B squared minus C squared divided by 2AB. Right there. Boom. You've already seen this in use. So this is the law of cosines. So you're thinking we substitute this here, get common denominators, factor, and then we'll start introducing this object here, and we can get to that very easily. So let's do it. So this is going to be 1/4 A squared B squared, and the A squared B squareds are going to absorb because of what's in the denominator. And so we're going to get a lot of simplification here. So now we have, again, 1 plus this. So let's just go ahead and do it. I mean, the thing is, the common denominator is 2AB, so we're going to have to multiply this 1 by 2AB. So we get 2AB plus A squared plus B squared minus C squared divided by 2AB. Don't we wish all algebra were this simple? Now, of course, we're going to get a common denominator, so we're going to again multiply this by 2AB. So we have 2AB, and now we have to subtract everything. So this is going to be a plus C squared minus A squared minus B squared, 2AB. So again, notice when we subtract the cosine C, all of these get negatives. So negative A squared, negative B squared, minus minus plus C squared. And then the common denominator 2AB. So again, fractions, general math, or what are we going to call it? Number theory. So now look, everybody, we've got a 2AB here and a 2AB here. We can just move these over, let it join the riffraff over here and get rid of the A squared, B squared. So this will be, so we got 2, 2, 2, 2. So that's 1/16. And we have A squared, B squared. And then, of course, AB times AB is A squared, B squared. So those are going to absorb. And now let's rearrange things. Notice here's a perfect square right here. This is a perfect square. This is a perfect square. This is A plus B quantity squared. Now over here, it's subtracted, so to speak. So I'm going to have to do a little bit more surgery on that. So I'm going to wait to write that down, but I'm reminding you what we're going to have here. So go ahead and write this in the correct order. So we're going to get A squared plus 2AB plus B squared, kind of section that off, minus C squared right there. And now we're going to shove all of this over to the other side. So we're going to say C squared and then factor the negative. This will be A squared minus 2AB plus B squared. So notice we're putting a perfect square over here, but we're factoring the negatives out of all of these. So this needs a negative, minus minus is plus, and then the minus minus we get here. So this is equivalent to this. And now I can do the same thing I did for this one. This is just now A minus B quantity squared, okay? So now we're using the identities from the very first day. This is really algebra 1, but you know, back in algebra 1, you didn't think this way. It takes a while to get up to this level of maturity, but once you get there, you're thinking, wow, now I can really use these identities to do some really great mathematics. So now let's go ahead and substitute these nice algebraic identities for this trinomial and this trinomial. Notice all we're left with is a 1/16. So that's going to give us all the 2's that we're going to need in the denominator, 4 of them. How funny. So now we get, well, let's use a bracket. So we get A plus B quantity squared. So we get another difference of 2 squares. That's going to give us all the A's, B's, and C's. And now here we have a C squared minus A minus B quantity squared. Okay, so notice perfect square, perfect square. Now we have another difference of 2 squares twice. So when I say factor, when I say factoring is essential and students don't want to do it, they don't want to learn Professor Ron's AC lemma, I'll say, okay, then mark calculus off your list. You don't want to learn trigonometry, mark calculus off your list. You don't want to understand conic sections and summation notation, well, mark calculus off your list. This is essential material. I'm not sure how it was assumed that since we all have calculators, that that's going to make math easier. No, we do the same thing. So what I'm trying to show you here, and when I do every single problem I construct in this class, I do it the same way. We use the same techniques. So if you're going to get any better, you have to start applying these techniques. Otherwise, you just keep rehashing the same stuff over and over. I take my notes from one semester, I throw them in the garbage can, and I take out clean sheets of paper and rewrite everything and add new ideas as I do research so that you get a fresh presentation. That's what you always have to do. You have to reinvent your mind every time you do something to get better, to improve. So now how can we use our identities? Let's go ahead and factor them. So this will be 1/16. And we'll break this up into 2 pieces. So we're going to have what? A plus B plus C. So when you factor this, this is A plus B plus C, and then we have A plus B minus C. So that's like an A squared minus B squared. A plus B, A minus B. Do the same here. C plus A minus B, and then C minus A minus B. C minus A minus B. So that's going to be a minus here and a plus here, the 2 double negatives. So when we do C plus A minus B, we get C plus A minus B. Then we do C minus A minus B, we get C minus A, but minus minus with the B. So this is the formula we're using. This is the generic formula. Remember, I'll use different letters. Say it's like when we say alpha squared minus beta squared. This is alpha. I'll do the plus since I did that first. Alpha plus beta times alpha minus beta. Okay? So we think of this as alpha. So we do A plus B plus C. Then we do A plus B minus C right here. Here we do, again, this flipped around. So this is the alpha. So we do C plus A minus B right here. And then we do C minus A minus B right here. And we get that. Because again, we have to distribute the negative to get this. Now you're seeing that's, if we go ahead and put these 2's under each of these, we can rig them. we're already going to get S right there, but we have to rig these. So let's go ahead and do some more surgery. So 16 is 2 times 2 times 2 times 2, right? So let's go ahead and fill that in. So we get A plus B plus C divided by 2 times A plus B minus C divided by 2. This one's a check. We already have the S right there. And then we get what? Let's do it in alphabetical order. A minus B plus C divided by 2. And then here we have a minus A plus B plus a C divided by 2. So now we want to rig this. We want to add a copy of B and then subtract a copy of B so that this will work. So let's do it. So this one's done. A plus B plus C over 2. And now we'll do A plus B plus a C. And then, of course, if we add a C, we have to fake it. We have to get rid of a C right there. So we have another C there. And here we need an A plus B plus C. So we do A plus B plus C minus 2B. And then we need a positive A. So we do A plus B plus C minus 2A. And now we're done. This is S. This is minus C, right there. This is S. This is minus B, right there. This is S. This is minus A, right there. We're done. So this gives us S times S. I'll do the A one first in alphabetical order. S minus B, S minus C, and we're done. You just take the principal square root and you have that. So I'll just say, take principal square root. So the key here is that you wouldn't expect this formula to be simple, as far as justifying, but this is a direct application of algebraic identities, the law of cosines, and the area formula that we already derived. So now you're thinking, man, this is how is it that all of this fits together so nicely? See, as new mathematicians invent more mathematics, it certainly has to be consistent with the ideas that have already been formulated and been shown to be correct. Okay, so if someone comes up with a new way of processing the law of sines, then a law of cosines or even law of sines, then it's like, okay, how does this impact Heron's formula? So they figure out that you can actually prove Heron's formula if you use the sine version of the area and the law of cosines, intermix, and then you get this object here, semi-perimeter. So I don't think mathematicians start out by saying, oh, okay, I'm going to define the semi-perimeter. Probably not a reason to define it. What they see is that when they work calculations, they see that it starts to appear. And that is usually the premise to say, okay, here's a quantity that comes up all the time. I'm going to give it a special name, kind of like the natural base. We see it comes up all over the place: finance, geometry, calculus, pi, another one. We give it a special symbol because we can't get away from it. So you may eventually come up with some construct in your work that you name, and it will be named after you, like the E is named after Leonhard Euler. Okay, so I mean, pi, I guess maybe pi should have been named after, call it something else. I don't know, the Greeks or Euclid, we already used E, but the idea is that the Greek letters are useful for that, and then E for Euler kind of thing. But the idea is now that we can see the intermix of the algebraic identities with the two new results from trigonometry right here. Okay. So how does this impact what we're going to be doing with your test? The test is fairly straightforward, and I think it's relatively when you compare it to the last test, I think it's probably not as hard. But of course, as I talk to you all during conference hours, it appears that, oh, this is different, Professor Ron, and because it's a little bit new, I think it might seem more challenging than it actually is. But when you're doing these, I want to note some things that you need to have, like you might have a unit circle, maybe you're using Professor Ron's unit circle, but there's certain ideas that come up over and over again. And central is the arithmetic of the unit circle, which you know. But what are those famous identities that I use every day? The Pythagorean identities. Now, when we think of these, we think of the fundamentals. So I guess, we can use theta, we can use x, use any letter you like now that we're flexible. Cosine squared x plus sine squared x equals 1. We started out using t's, right? And then we used thetas. Now you can use any letter you like. And then we have what? 1 plus tangent squared equals secant squared. Again, an identity is an equation that is true for all values of the variables for which it is defined. And then we have 1 plus cotangent squared equals cosecant squared. So these turn out to be very, very useful because we rehash them over and over and over. So here's an example. We'll say, write, in this case, we're going to say tangent, I'll use theta this time, tangent theta in terms of cosine theta, where theta terminates, or we'll just say terminates in the second quadrant, okay? So when we think about inverse trig functions and we think about solving equations, we always have to respect the arithmetic. So first off, when we look at this and say, okay, well, what does the hypothesis give us? Notice in this case, we can just do a little parenthetical. We know cosine theta in the second quadrant is less than 0. We know sine theta in the second quadrant is positive. So this implies, since the tangent is the ratio of these two, that it must be negative also, like the cosine. So that basically gives us the construct of the sign conventions. So whatever expression that we achieve, it should express that sign. That is, it should be giving us a negative value in the sense that if we actually evaluate it, we get the appropriate sign. And it may be embedded in the algebra. We may not necessarily have a sign that's standing out, oh, I'm negative kind of thing. Just remember that a variable like x or theta can have a value that's less than 0, but it may not be reflected in a negative that is to the side of it. So that's important. So now what we want to do is say, okay, well, what does this mean? Well, we know in this particular case that tangent theta is sine theta, our friend, over cosine theta, right? So now when we look at this, we're thinking, okay, well, the cosine gets a check because we want to write, in this case, tangent in terms of cosine, but the sine is not cosine. So we're thinking Pythagorean. So we go up to our list here and think Pythagorean. But notice, Here's our little sidebar. We know that sine squared, and we'll use theta here, sine squared equals 1 minus cosine squared. And now the convention says that the sine of theta will be what? Positive because of the termination of theta in the second quadrant. So this means select sine theta equals the principal square root, that is the square root of 1 minus cosine squared. So we select positive square root because of this convention. And so now when we go here, we can make a substitution. So we have the principal square root of 1 minus cosine squared theta divided by cosine theta. Now this is fine because we know the cosine is negative. The principal square root is always positive. So this has the correct sign, okay? And again, it's not obvious. There's not a negative sign in it. Some of you think that the only way something can be negative is that it has a negative by it. That's clearly false, okay? If you're working with variables, it depends what the variable assumes, okay? X can assume positive and negative values in this type of an equation, or theta can, okay? So you can't just look at this and say, oh, well, there's got to be a negative there. That's just like saying, for instance, if I have the additive inverse of X, that could clearly be a positive number. For instance, if X equals -3, the additive inverse of X is 3. Negative X is positive. So dispel that fallacy in your reasoning, okay? It's something that I see when I teach calculus, and I'm befuddled by it. Don't put something there that isn't, okay? It's like when you're doing WebAssign and I get the messages that say, well, it's telling me I'm wrong. I said, but you're approximating your answer and no approximation has been requested, okay? If there is no approximation requested, you give an exact answer. If your problem requests that you round to a certain number of decimals, that you actually are to do an approximation, then by all means do it, okay? But do not add something to the problem that's not there. That's why it's important as you work through this that you think about the arithmetic of the unit circle, that it is what it is. It's basically, what is our new thing for general math? Number theory. First quadrant, when we think about this, and this is so simple, it's difficult. We know X is positive, Y is positive. X is negative, Y is positive. Sine, cosine, sine. Third quadrant, both negative. If it helps to just write this down on a note card, then do it. X positive, Y negative. It's that simple. So there's certain arithmetic conventions that have always been there. They've always been there. It's just now we're connecting them to the trig functions. Okay, now, one thing that's actually quite important when we started working with the inverse trig functions, you're fine with graphs. Graphs are easy. Those are just transformations. That's the simplest thing we've done, basically because it's just rehashing what we did in college algebra, and you saw that twice because we reviewed it. So that's something you should have fairly comfortably. But let's look at some of the inverse trig functions. Inverse trig functions. Now, a very popular type of problem is to use the right triangles when they're convenient and the inverse equations. Okay, so when you have inverse equations where you think, okay, you apply the function to its inverse, you think that just collapses. Okay, well, in general, it's very simple. But with the inverse trig functions, we have to what? We have to obey the range and domain as how we've defined them. So let's look at an example. Here's an example. And when you compute these on the test, it'll just say compute without a calculator. And then of course it'll say show reasoning to arrive at your conclusion. Show the steps. Why did you make this deduction? Okay. So you can't, for instance, if you write an answer and maybe it's not a very detailed, reasoning, but you need to say, I'm using the inverse equations and say, okay, this fits the definition, so to speak. So I'll say compute without calculator. So here's an example. Say we have the, let's try one that's actually kind of interesting. So we'll say the inverse sine of sine. In this case, we'll say 5 pi over 6, okay? Now, the first thing you could do when you look at this problem is say, oh, those are the inverse equations. So first, you do a little sidebar. And you think, well, how do we define the inverse sine? Okay, first, you don't have to draw the graph, but I just want to review this. We know what the graph is. It's a nice odd function. We know the inverse sine function is odd. Again, not Rembrandt, clearly, right there. So this is y equals inverse sine of x. And then that's our definition. Then we know that sine inverse of sine x equals x if and only if x lives where? Between negative pi over 2 and pi over 2. That's the premise behind the definition of the what? Inverse sine function. So if we want our collection, if we want our computation to collapse, then we have to make sure x lives where it needs to live. Now, this is where we can be a little bit more selective. So now we notice. So we say observe. 5 pi over 6 does not live there. Okay, so first what we can do is say, okay, can we adjust this? Can we adjust by a reference angle? Can we adjust for an equivalent value of this sine that will give us a particular value that lives here? So again, we note, so we observe that sine, well, for instance, sine of 5 pi over 6. Again, this is, I'm doing all this in detail so you'll have some good notes. This is in the second quadrant, right? This is second quadrant. And we know in the second quadrant that the sine is positive. And it has an equivalent value in the first quadrant. So we have to use the reference angle. So this will be sine of pi minus 5 pi over 6. In this case, if you want to say, if you want to call this theta, we'll just say that this, I'm not giving it a name, just say reference angle. I didn't call that theta, I could call it theta hat. So we know these are equivalent. So this would be a way to adjust the input. Again, there's no given rule to do it. You just simply adjust the input based on what you know this must be. And so now when you do this computation, this will be a 6 minus a 5. So this is sine of pi over 6. But we notice that pi over 6 does live here. It's in the first quadrant. And so we can say pi over 6 lives between negative pi over 2 and pi over 2. So now we can go back to our calculation. Inverse sine. This is where you can't just say, oh, it's not defined. Well, because the sine function is defined for any real number. Okay, so we don't have the luxury of calling it undefined because the inverse sign is not what's on the inner function. So that's what makes this problem harder. So now we know this equals inverse sine of pi over 6. But again, pi over 6 lives here, so we can collapse to x. Here is our x, so we get pi over 6. The answer is not 5 pi over 6. I have students send me messages, why is this wrong? I'm like, well, you violated the definition of the inverse sine. Okay, so when I say you need to know these definitions, you need to have them on note cards, and it helps just to write them down just to practice with them, because these are the objects, okay? When you get to calculus, especially calculus 2, you must respect the ranges and domains, because when you talk about the derivatives, you have to use that arithmetic to make sense out of the formulas. If you don't, then what you're doing has no relevance. I mean, you're just making it up, and you might as well draw lines through it because it doesn't make any sense. The idea behind trigonometry, or the idea behind higher level mathematics, is that we make new definitions that are less simple. And as you get more advanced in your mathematics, the definitions get more and more complicated, and they also get more abstract. So you have to think about it. We've defined the trig functions in a very abstract way. There's no equation. We have equations that combine, that characterize the trig functions, but we don't have a formula that says this is how you compute sine. We figure out in calculus that you can derive decimal approximations for sine functions or trig functions once you develop their infinite series. So these are very strange functions, very, very strange. So when we think about this, we're like, we breathe a sigh of relief. Now for a simpler type of example, so if you were working a problem and you had something like this, say you had inverse sine of -1 over the square root of 2, and you were working a problem and this was part of it, you're thinking, okay, we proved in class the inverse sine is odd. So we're going to use that. So if we wanted to compute this, just as a little simple example to remind you of the definition here, this is definitely defined. Why do we know this is defined? What is the domain? The domain is -1 to 1. This is defined. This makes perfect sense. So now we're thinking, okay, the inverse sine is negative because we're lazy. And now this is a value, this is a terminal point. This is the y coordinate of a terminal point in the first quadrant, namely the terminal point that corresponds to pi over 4. So we simplified the construct by using the fact that the inverse sine is what? Negative. Then we extract the negative, odd, so we can extract the negative, and now we can apply the first quadrant of the unit circle. So this will give us the negative of pi over 4. So when we compute with the inverse trig functions, it's going to be the same way. We can use our calculators when we don't have points that are on the unit circle. That's why when we're doing the triangle problems, we go to the what? We go to the Google calculator to get a nice approximation, because again, if it's not on the unit circle, then we don't have a tangible value. So then we have to use the fact that the calculus gives us the actual decimal approximation, and that's where we use Google, which again, otherwise, like I said before, we'd be using tables and slide rules, and that's really not available to us. So we get to use Google at the end of the problem. Now, of course, if you're looking for an exact answer, then you just leave it alone. You just leave it alone. If it doesn't end up to be a nice value from the unit circle, you just write it in symbolic form. It's like saying, okay, say the answer is for x is the square root of 3. Okay, you could approximate that, but if you need an exact answer, you're done. We think of the same way with inverse trig functions. For instance, if we had a value that was not on the unit circle, say we had, say, the inverse sine of 1/3, okay? That's not a value. That's not the y coordinate of a terminal point. So we'd stop right there. That's exact. It's defined, but it's not a number that we know. Now, of course, if you're doing an applied problem, you can go to your Google calculator and it'll give you a nice Google approximation. Okay. So when the problem needs exact, leave it exact. This is this symbolic representation for this value. That's exact. So we say exact. We say exact. So when you think about this, what you do with not a moment's notice. You do it. Okay. Think of this the same way. Now, a lot of you you come to office hours or conference hours and you're like, oh, Professor Ron, we got these equations. What's up with the equations? Well, look, the simple equations we've seen with the law of sines, but simple equations can be done using the unit circle. Now, of course, when we get to the end of chapter 7, we'll do more advanced equations that require more algebra and more identities. But for right now, you should be able to navigate very simple equations. So here's an example. And that means you're going to have to use your inverse trig functions. So let's pick on a cosine function. Okay, so what I'm going to do is I'm going to say solve in, we're going to say the unit circle. We could go like 0 to 180 degrees or 0 to pi or 0 to 2 pi or 0 to 360 degrees, just depending on what the problem says. So we could say solve in 0 to 2 pi. So we have something like that. So we want to find all solutions that live here using our unit circle and anything that we know about trig functions. So here's an example. Say we have, here we go. We've got 2 cosine theta. Let's see here. We'll say plus 1 equals 0. Something like that. So you had some of these in section 4 of chapter 6, but I'm going to bump it up a little bit and say, well, you can do basic algebra. What does this mean? Okay, when you look at this and you want to solve it in the unit circle, you're thinking, well, those look like some nice numbers. I bet those are on the terminal points of the unit circle. So equivalently, very simple, we'd say 2 cosine theta equals -1. Okay, that's relevant. And then we can divide by 2. -1/2. Now, here's what's interesting. And this, I was talking with a student yesterday, and their question was, I'm having trouble with this problem. So I thought about this when, of course, I was making out the test, because I think about the questions you ask, and I think about what I teach. And you need to know what I teach because it's important, because I know what you're going to need for calculus. So the first thing we thought about, if we're going to apply inverse functions, that is the inverse cosine, we've got to say, okay, let's travel back to how we defined inverse cosine. So remember, inverse cosine of x. So this is y equals inverse cosine. So what do we have? We have domain is -1 to 1, okay? Now, of course, if you're solving an equation and you violate the domain, you just say no solution. And you're thinking, I'm not going to be that easy on you. So I won't make it that simple. But some of you may ignore the domain and try to solve it anyway and get a bunch of hash. You go, what's wrong here? Okay, well, that may be instructive, but I'll just say this. If I ask you to solve an equation on the test, it will have a solution. I want you to get a solution. So what is the range? The range here is 0 to pi. Again, this is a definition. This is how we define the inverse cosine. We restricted the domain of cosine to make it 1 to 1. Okay? And once we have a 1 to 1 function, we automatically have a reverse path. that reverse path we call the inverse function. And so what did it look like? So this function doesn't have the nice qualities of the inverse sine, but it still has good qualities. So we have pi over 2. So you all probably know all of these already. I'm just reminding you. And so let's draw it. There you go. So this is y equals inverse cosine of x. Now this, remember, this wasn't an odd function. We have inverse cosine of the additive inverse of x is just pi minus inverse cosine of x. So this is not a nice, we get most of that with most of our inverse trig functions. They don't have the nice odd characteristic that the inverse tangent and inverse sine have. So sorry about that. And it is a bummer. It is a bummer. But like I said before, if you ever need to just refresh your mind about inverse trig, especially even when you get to calculus, go to the Wikipedia page. It is a great summary of all things that you need to know about inverse trig. There, some of those Wikipedia math pages are excellent. They are free. I mean, free. I mean, even if it were lousy, it's still free. But I've looked at these and I'm thinking this is such a wonderful resource. And so again, you always have resources that you can take advantage of when you just want to think of some new ideas. But I think I've given you enough ideas for now. And then as you grow in your mathematics, you can add to it. So when we look at this, we're thinking, well, this is defined because now when we look at this, we have cosine theta. Thinking about this where it is, this is in the range of the cosine function. So this makes perfect sense. So it makes sense to apply the inverse cosine. This is defined so we can move forward. So if and only if theta is the inverse cosine of -1/2. Now, this is where we think about what's going on here. This is basically Professor Ron's lemma. So we think, okay, well, notice this is going to be a second quadrant angle because now what we see here is that when we map to the inverse cosine, we run from 0 to pi over 2 and then pi over 2 to pi. And then the values between pi over 2 and pi give us the negative values. So the looking here, going backwards, if we've got this, we end up here in this area. But this is a unit circle value. And that's why I've been good to you. You don't have to use your calculator. So you won't need a calculator for this. No calculator allowed. So then when you look at this, you think about the terminal point. So we observe the terminal point, -1/2 √3/2. That's the terminal point that corresponds to this computation here. And then you say this corresponds to what angle? Well, that angle is 2 pi over 3. In your unit circle. So it's like you think of reference angle. If you're here pi over 3, that's 1/2 √3/2. That's no good. So you look into the second quadrant, -1/2 √3/2. So the inverse cosine has to be respected. We have to look for values that live in the range of the inverse cosine. Now with inverse sine, it's negative pi over 2 to pi over 2, okay? With the cosine, it's pi all the way over, 0 all the way over to pi. So now when we write this, we have theta equals 2 pi over 3. Now, this is where I was talking about Professor Ron's lemma. There's another value, and this, the simplest way to look at it is to think about the unit circle and its symmetry. Of course, we'll just have a formula to use, but I want to give you this just as some extra insight. This is usually a train wreck, because when you think about this, we need an algebraic way to find that other solution. But if you think about this symmetrically, we'll draw this angle here. This is 2 pi over 3. The point is negative 1/2 root 3 over 2. But symmetrically, there's another point on the unit circle that corresponds to a value in this range that also makes this true. So this being 2 pi over 3, and then also this point here, negative 1/2 root 3 over 2. Well, of course, you can look at this just in terms of the symmetry here. This implies, and we can call alpha, if you want, alpha equal 2 pi minus 2 pi over 3 is also a solution. So this will be 6 pi over 3 minus 2 pi over 3, which is 4 pi over 3. So if you just look at your unit circle, you can see that we have a second solution in 0 to 2 pi. So we'll say here, 4 pi over 3. So this is kind of an introduction to solving equations that makes basic use of what? The inverse trig functions and the symmetry of the unit circle. Because again, I was also talking to the students saying that if we can just exhaust the unit circle, then we can extend by multiples of the period and get all the solutions. But the key is that if you stated this problem and say just solve in 0 to pi, then that'd be it right there. 2 pi over 3, that'd be it. No more solutions. But when you extend to the entire circumference of the unit circle, you pick up another solution. That's the same way with the sine function. So this is basically Professor Ron's lemma. When you have a solution with the cosine equation, the second solution will be said solution subtracted from 2 pi. Now with the inverse sine, it's a little bit more complicated, and we'll say more about that as we get to the end of chapter 7. But something like this is very important. And what I want to emphasize here is that the importance is based on how we define the inverse trig functions. So when you define an inverse trig function, that opens the door to a solution, one solution. An inverse function is 1 to 1. So if you solve in the range of a 1 to 1 function, there is exactly one solution. If there is one, if it's defined. Then we're thinking, well, the unit circle gives us functions that aren't 1 to 1. So if we're going to abide by the arithmetic and the symmetry of the unit circle, we can start the ball rolling with the inverse trig function to get a solution, and then we can adjust to find a second one that we know exists, which is right here. Now, why do we like this construct? Because if we have a formula here or a value that's not on the unit circle, then we can only write it symbolically. We can only write it symbolically, and then we could use our Google calculator to approximate it. But symbolically is better because it's like doing the triangle problems. We have all of the nice equations that are exact, and then we do one level of approximation. So now when you solve this equation in 0 to 2 pi, you have not only 2 pi over 3, but you have 4 pi over 3. So the beauty of this is that we could have talked about this after I defined sine and cosine, which we basically did, just going backwards and forwards. When you define the inverse trig functions, then you automatically have solving of equations. I mean, even before you define them, you can think backwards, but now we don't have to think backwards. The inverse trig functions give us the what? They give us the reverse path. So again, this kind of argument is actually very essential and one that you should be able to do. And we'll do a lot more with this when we get to the end of chapter 7, when we look at applying college algebra to more sophisticated equations. But here, ladies and gentlemen, this is the foundation right here. This kind of sets the stage for everything. If we have to apply some more elaborate algebra, we still have to go back to those base equations, work with the base equations, and then extend as we see necessary, like maybe the zero product, anything like that that we've been doing in college algebra. All of this is the same. And fortunately, all of those techniques will apply. It's just now that instead of having x's and algebraic functions and logarithms and exponential functions, we now have what? Trig functions. So the objects are the same, but how we combine them has certain particular characteristics, like logs have identities that allow us to combine logarithms. Trigonometric functions have identities which will allow us to basically rewrite them so that we can make more use of what we're doing. And why has the trig become so important? Because it connects distance and angular measure. And when we think about motion in our space, we think about how physics is developed, trigonometry is an essential tool. And so you're thinking, and I'm sure of this when you took your number theory class, your general math class, you started with triangles, and now we've developed to the unit circle, which we find to be actually quite useful when we're doing these types of computations. Now, one thing that I said before, when you're solving triangles, we can use the more elaborate schemes of the law of sines and the law of cosines, but I told you I wasn't including that on this test. But we can solve right triangles. So let's do it one of those. That is simple. And we can compute areas of triangles using the 1/2 AB sine theta. Of course, if you want to use something from law of sines or law of cosines on the test, I don't think you're really going to need it. But if you want to use it, be my guest. I mean, and of course, if you've studied that, that's going to help you in more understanding, but it won't be required. Again, I'm trying to give you a little bit more cushion of time. So when we think about right triangles, we think super simple. So let's look at one. So here we will suppose C, again, it's going to be the generic labeling. In this class, we always use the generic labeling. So we'll have the uppercase letters for the angles and the lowercase letters for the lengths of the sides. That will always be in force. So you must assume that. So we're going to suppose that C is 90 degrees. So I'm just going to draw the generic triangle here. Not necessarily to scale. So we've got C here, this is 90 degrees. And this is a given, and also given in this particular case. So here's C, I'll put A here, and I'll put B here. And we're gonna be given, so here's A, and here's B. Given A, in this case, will be 3, and B will be, I'll just say 5. So this is just a generic example. So I'll say solve the triangle. Now, and notice degree mode. You know how to convert between radians and degrees and vice versa. But the thing is that when you're working with triangles and you're trying to find nice approximations, the degree mode is a very much a luxury that is very useful. And I certainly support it. So when you go to your Google calculator, make sure you're using a degree mode if it is asked that we round to 1 decimal. So I'll just say for the summary, just like I've been doing before, the summary will be round to 1 decimal once we have our exact equations. All right, so summary will be like what I've been doing. So just kind of keep that as a sidebar that we will apply at the end of the problem. So now go ahead and mark what we have. we have A equals 3, and we have B equals 5. So now, if you like, we can go ahead and use trigonometry to solve for the other angles. We know C, let's go ahead and put this in. This is 90 degrees, so how funny. So now we can say, okay, well, angle B, we can just use the tangent function, opposite over adjacent. So this implies B, well, let me write the tangent function. Tangent of B, which is opposite over adjacent, equals 5 over 3. If and only if B, again, the tangent, the range of the tangent is all real numbers. Tangent is the nicest function you'll have in trigonometry. It is so devoid of issues, okay? It's odd. It has great characteristics. The inverse trig function is defined for all real numbers. You can't mess it up, even if you try. Now, for sine and cosine, you can make all kinds of mistakes. So this will be the inverse tangent of 5/3. This is exact. Again, degree mode. So we got that. And don't you wish that the generic triangles were this simple? This is very easy. So now angle A, so we've got, this implies angle A will now be 180 degrees. Well, these are complementary, so we can just, let's just say they're complementary. We won't do all this work, too much work. Just forget the 90 degrees. You could write it down if you want. So this will be 90 degrees minus inverse tangent of 5 over 3. So this is so much easier than the general law of sines and law of cosines. Those are much more complicated computations because we don't have the luxury of the right triangle. So here we have angle A, exact. Exact. This is what I want to see on your paper. I do not want to see mounds of chicken scratch, okay? I want to see deductions. I want to see how I have taught you. So if you spend time with the lecture videos and the SmartPen videos, you will know what I expect of you. So I don't want any more messages about what do you expect. You know what I expect. That has never been a question. I teach consistently. I teach every problem in a consistent manner because I know the consistency is important. Sometimes you might think I beat a problem to smithereens, and I do, because my students will say, oh no, here he goes again. He says, well, what about this? Or what about this? And we do a problem. Well, what if it were this way? And they're like, well, here he goes again. I said, but no, kids, I want you to think about what the problem is asking us to do. I want you to think about the mathematics that's involved. Because if we don't think about these things, we make incorrect conclusions. And if you got a STEM job, you may do something that will harm people. Okay, you work at a major chemical plant. You make a bad calculation and you don't have your colleagues check it, and then the boiler room blows up or something. You have to be careful. Okay, I'm harder on myself than I am on you as students. But the thing is, we have to make sure that we check our work, and then we pass it to our colleagues and they check the work. You all help me make sure that my work is correct, because we have to work together in a lecture. Unfortunately, when you take a test, you're on your own. That's why when you get your job, life is going to be easier because you'll have people around you that are smart like you, and then you get paid for it. How nice. Is that not the best way to be doing something you love to do and get paid for it? That is a remarkable thing. And a lot of you have your part-time jobs, and maybe it's not the job of a century, but you're glad to have it. And it puts money in the pocket. It helps you to have a better life. That's what we're looking for. So now when we look at this, we're thinking we've got the angles. What's the only thing left? Pythagorean theorem. So now we have c squared will be 3 squared plus 5 squared. So again, we'll have 9 The easiest calculation so far, right? This will be 34, if and only if C equals the square root of 34. So we take the principal square root, exact. So what we're seeing is that the law of sines and the law of cosines build in the inverse trig function, don't they? They build in inverse sine for law of sines. And then, of course, they build in inverse cosine for law of cosines. And then we have to respect where the angle is going to be. Well, between negative pi over 2 and pi over 2 for sine, and then for inverse cosine between 0 and pi. So we have to respect that as we're doing the problems. So that is a complication that reminds us of what I just did here, okay? So now we can do our summary. We're going to go to our Google calculator, so let's do our summary. So now that we've done the other more complicated problems, this seems actually quite simple. So we're going to have a we're going to have a B and C, and of course we'll just do a 1 decimal approximation. So let's go to Google. You know, I'll be honest with you. One of my former students in pre-calgebra, we used to have I'll go in the wrong place. We used to have a real popular course that combined algebra and pre-cal. And ladies and gentlemen, that was college algebra, which is a 3-hour course, and pre-cal 7 in one semester, a 7-hour course. The students meet every day or 4 days a week. Bam, 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 bam. And I had a student that would say, oh, can I use Google? I said, what do you mean Google? Oh, there's a nice calculator. And the student now is at UT majoring in engineering. One of the, I used to call him, his name was Ron. I called him Professor Little Ron because he was extremely talented. So I say, Professor Little Ron, where did you get that? Where's the Google calculator? And so this is why I use this in my teaching, because it is so convenient and such a wonderful tool. So again, here for the Google calculator. So again, go to degree and make sure that's highlighted. Let's go ahead and do B. So B will be the inverse tangent. So inverse tan, remember arc tan, that's the alternate expression for inverse tan, which of course I don't use. 5 divided by 3. Close. And this gives us 59.0 degrees to 1 decimal. So B is 59.0 degrees. Now, of course, since this is, this is where you can save some time. Since A is just, we subtract this from A, just go ahead and subtract 90 and take the absolute value. I was telling a student this, if you're running out of time, just say minus 90, and this will give us negative 30.96. So this is actually going to round up. This is going to be to 1 decimal. This will be 31.0. So we get 31.0 degrees when we round to 1 decimal. So see that negative there? Just ignore it. If you've got it stored and you've only got one calculation where you basically subtract the previous calculation from 90, just do it in reverse and take the additive inverse of it if you want to save time. Now, again, if you don't like doing this, I'd say, well, forget that. And I would say 90 degrees. That didn't make any sense. Minus inverse tangent. And then we'd do 5 divided by 3. And of course, Google is doing the conversion to degrees, so we don't have to multiply by 180 over pi. And that gives us the 30.96, which rounds to 31.0. Okay, so if you prefer to do it that way, that's fine. I thought maybe if you need a little time saver, but maybe you don't care about that. And then of course, the square root of 34, we can get a 1 decimal. That's going to be pretty close to 6. So this will give us 5.8. So again, don't get used to this. Don't get used to these simple right triangles, because we know that the generic cases are anything but simple. It's not that they're overly difficult. It's just that all the components come into light. We're thinking, Do we have the ambiguous case? I mean, if we have a second solution to the sine equation, does it actually give us a legitimate triangle, or do we violate the degree sum? So there are lots of pitfalls with that case. With the other cases, we just have either one triangle or no triangle. Why would we have no triangle? I remember Jay was asking about this. If you have an equation that you can't solve, then you'll see, oh, I can't solve this equation. Or maybe you just don't quite see that and you go to Google and you try to solve it and you have an error. If you see error, just make sure that you entered everything correctly. Well, if that's the case, then you violated the range and domain of the trig functions. For instance, if we had, so here's the end of this. So this is what you would put on a test. This is what I'm talking about. Say you were doing a triangle problem and you end up, say you get cosine of B. So you're trying to find angle B equals 3, okay? You look at that and say, that doesn't make any sense. Now, the thing is, why does this not make any sense? Well, for one thing, when we define cosine of x, cosine of x, the range, is the opposite of the inverse cosine. It lives between -1 and 1. Okay, so this is not defined. Well, say you don't recognize that and you say B equals inverse cosine of 3. Well, again, the domain, that's, well, I don't need to write this again. Let me just do this. This is the domain of the inverse cosine. I'm abusive with the letters here, but see, either way you go, you're going to get an error. So this is undefined. So if you're working, so we say no solution. So if you're working with a triangle problem and you end up with an equation like this, then that's the case where there is no triangle. Okay, it doesn't make any sense. Now, the idea is that with the ambiguous case, you can actually get additional equations and you'll get valid answers. You'll get valid answers. The equations will give you valid answers, but they will violate the internal degree sum of a triangle. If it exceeds 180, then it's not a triangle. So we have to be a lot more careful with the generic triangles. But the beauty is, it's kind of like saying, here's another example. It's kind of like saying e to the x equals -2. Well, you can abide by that and say, okay, that looks kind of odd. E to the x has a positive output. So we'd say undefined. So when we start thinking about this, because we know e to the x lives in 0 to infinity, the positive reals. So it's the same thing going on. So you know how to do this, therefore you actually know how to do this. You just have to be familiar with the inverse trig functions. If you know the definitions of the inverse trig functions, that automatically reminds you about the regular trig functions that we started with. So if you know the inverse trig functions, ladies and gentlemen, then you just kind of kill two birds with one stone. So what you should do is have those written, the ones that we use a lot: inverse sine, inverse cosine, inverse tangent, inverse secant. When you get to calculus, you will use those. The other two, it's not to discriminate. It's not a problem. Just remember that when you get to calculus, we've already talked about this. These are the cofunctions. Inverse tangent plus inverse cotangent of x equals pi over 2. This basically says that the derivatives are negatives of each other. And that's why you spend more time with inverse tangent than you do inverse cotangent, because equivalently, and we proved the one about inverse sine plus inverse cosine. I keep going back to that because that was not a simple proof. We have inverse cotangent of x equals pi over 2 minus inverse tangent of x. Now, of course, when you get to calculus, you will learn about differentiation. The differentiation operator is linear. So when you take the derivative of this implies, and this is what you're going to learn in calculus, that the derivative with respect to x of the inverse cotangent of x will be the additive inverse of the derivative of the inverse tangent. And so if you know that these are just negatives, you're like, no big deal. That's not going to give you a new integral formula because they're only going to differ by a negative sign. So it's the reason we just don't give those functions as much time. It doesn't mean they're unimportant, but we see by using an identity from pre-cal, we actually get an identity in calculus. And I mentioned this when I teach Cal 2, but they said, we never did that in pre-cal. Well, that's okay. Pre-cal classes can vary, but the idea is what I keep seeing in calculus is that students know very little trig. And I have to kind of, okay, here's the trig. Let's remember this. Let's remember this. I don't want that for you. I want you to get to calculus and I want you to have a good understanding. And if you have to go back and highlight some things, that's fine because you're not going to remember everything. By the time you get to Cal 2, you'll probably have forgotten 60% of what I've taught you, if not more. Because with every month that passes, you lose your keen idea of what's going on. That's what I have to tell students that they don't seem to understand. You have to review your work. If you go the whole summer without taking math, I can assure you that when you take the next course, you will be in a deficit because you haven't done any math. All of the more intricate things that you mastered, you would have forgotten. And if you have committed some of it to long-term memory, you may be able to revive that, but with effort. So it's kind of like having a job. If your boss says, okay, you need to be up on this because I'm going to require this, in the next 4 or 5 months. So you're going to have to take care of this. So what are you going to do? You're going to review it. Okay. So think about classes in the same way you would think about a job where your boss says, okay, make sure you do this. Now that's a responsible thing to do because number one, you want to keep your job. And number two, you want to do good work. So I even did that when I was an undergraduate at Carolina and I would have the summer off and I would work and whatever. I had to work a whole lot harder in the fall. And I kept thinking, man, I need to do some review. This is crazy. So after that, I made sure I either did review or I took a summer school class just to keep my mind moving. Okay. Because we all like to take a break, but too much break, you get cloudy up here. Okay. So the test is available. I will send out email invitations for my office hours. I always say conference or office hours, the same thing. I have 3 today. My goodness, what was I thinking? And then I have 1 in the morning. And so, of course, now your test is available. Remember, when you complete your test, you scan your work to make one file, and you upload that on Blackboard with the Turnitin app. Again, I appreciate your attention to that. It is important that you do that. By now, I expect everything to be okay. Like I say, you know what to do. And take advantage of that. It gets your test aligned with your test work. And that way, when I assess, I've got both of them and I can give you more attention. Ladies and gentlemen, it takes quite a bit of time to grade your test, okay? Because I read everything that you write. And if you get deductions, it's because you left gaps in your reasoning or the reasoning was incorrect, okay? So I'm trying to help you get better. It would be certainly easy for me just to say, check, 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 and that'd be done. But that's an absolutely irresponsible way to teach a math class. Okay. I need to see that you understand the work. And so you know what the rules are, you know what your obligations are. So have the integrity to stand and do your work and own it. And no more complaints. I'm getting a little bit winded of complaints because you are in a STEM math class. The standards are high. Ladies and gentlemen, this is San Jacinto College and the standards are high. Again, our president, Dr. Williamson, a wonderful, wonderful scholar who supports the academic integrity of this institution. and I will continue to do so. And with that said, I wish you well as you prepare. I wish you Godspeed as you do your work. Make sure that you have a good window of time to do it where you're relaxed and the anxiety is low. So if I don't see you at the conference hours, I wish you well on your test, and everybody have a great day and enjoy our wonderful spring weather. Bye, everyone.